Now, let us try to find out the arc length and volume element in curvilinear coordinate system. Let us consider a position vector r is given as a function of u1, u2 and u3 coordinates in that curvilinear coordinate system. Then we can write dr as in the first notation del r del u1 du1 plus del r del u2 du2 plus del r del u3 du3, which is nothing but h1 du1 e1 unit vector plus h2 du2 e2 unit vector plus h3 du3 e3 unit vector. Then the differential of arc length ds that can be determined as the arc length that is given as ds is nothing, now we obtain ds square actually, ds, this quantity square would be dr dot dr. So, we will obtain this quantity, and if we have an orthogonal curvilinear coordinate system, we will have the dot product of a unit vector with itself being 1 and the dot product with another unit vector will be 0. This will be the expression. Therefore, ds squared can be written as h1 squared du1 squared plus h2 squared du2 squared plus h3 squared du3 squared, this way. Although this will not hold for non-orthogonal coordinate systems. Now, along a u1 curve, u2 and u3 are constants. So, if we consider a curvilinear coordinate system where this is the u1 axis, this is the u2 axis and this is the u3 axis, something like this, just a simple picture. And if we have along this, if we have an orthogonal curvilinear coordinate system, then along the curve of u1 we will have the other components, that is u2 and u3, those will be constant, necessarily they will be constant in a orthogonal system. On that line dr will be given as h1 du1 e1, and the differential arc length ds1 along u1 at any point p can be given as h1 du1. this is given as h1 du1. Similarly, if we go along the coordinate axis u2, we will find that ds2 is given as h2 du2 and ds3 along the remaining axis is h3 du3. Once we have this, then the volume element dV can be given as a product of these components. What kind of product gives us a volume element? It is the scalar triple product that we all know. That means, the volume element can be given as h1 du1 E1 unit vector dot H2 du2 E2 unit vector cross H3 du3 E3 unit vector, like this. And because triple product can have a negative sign if we have a particular order, and we do not want a negative sign because volume element, we want a positive volume element. So, we take the absolute value of this, and this turns out to be H1, H2, H3, du1, du2, du3. This happens like this because we know that in orthogonal curvilinear coordinate system, we will always have E1 dot E2 cross E3 equals the absolute value of this will always be equal 1, because they are unit vectors. Now, let us consider the gradient, divergence and curl in curvilinear coordinate systems. Suppose phi is a scalar function and A is a vector function given as A1 E1 plus A2 E2 plus A3 E3. It is a vector orthogonal, it is a vector function of orthogonal curvilinear coordinates u1, u2 and u3. Then we will have for gradient of phi, that is written this way, is 1 over h1 del phi del u1 E1 unit vector plus 1 over h2 del phi del u2 E2 unit vector plus 1 over h3 del phi del u3 E3 unit vector. For divergence of the vector function A, we will have This would be given as 1 over H1 H2 H3 del U1 of H2 H3 A1 plus del U2 of H3 H1 A2 plus del U3 of H1 H2 A3. And finally, for curl of the vector function A, it is given as 1 over H1 H2 H3, the determinant of H1 E1 unit vector, H2 E2 unit vector, H3 E3 unit vector, del U1 del U2 del U3 H1 A1 H2 A2 H3 A3, this determinant. This gives the curl. Let us also write down the expression for the Laplacian. Laplacian of a scalar function, that is del squared of phi, can be given as 1 over H1 H2 H3 del U1 of H2 H3 over H1 del phi del U1 plus del U2 H3 H1 over H2 del phi del U2 plus del U3 H1 H2 over H3 del phi del U3, like this.